As I said, my name is Appa. I'm co-founder and director at Xenotech, and today I'm going to give you some insights regarding HPC. And I do realise this isn't formally a SIG, but we're proposing a short course on the topic. So this should give you some highlights of the kind of topics which we would address in this type of course. For those of you who are interested, the picture that you're seeing there is more high-performance computing as art. That's the installation at Barcelona Supercomputing, where their computing infrastructure is installed inside an old church. So it's not always about just the science, art seems to come into this as well. The focus of my talk today really is just going to be based on the back of a report from NASA called NASA CFD Vision 2030. And I'm going to pick two items from their top 4 findings and sort of dive down a little bit deeper into those topics. The two very specific lines that I'll pick onto is the second and fourth line on the slide that you can see at the moment, and I'll read those out. So the first one is HPC hardware is progressing rapidly, and technologies that will prevail are difficult to predict. My first part of the talk will be addressing that particular comment. And the final one, which I'll be addressing, is revolutionary algorithmic improvements will be required to enable future advances in simulation capability. And both those statements apply both from an industrial point of view, from CFD, but also, I believe, from a scientific and academic viewpoint as well. So where did we start off in terms of HPC? The picture that you can see in front of you is from the 1950s. And that, believe it or not, is a 5 megabyte hard drive. And in those days, that cost nearly $10,000 per megabyte if you wanted to store that amount of information. So 5 megabytes today, just to remind you, your phone in your pocket probably stores at least 6 gigabytes, let alone a megabyte. But that's where that kind of technology was starting from the 1950s, and you can see the progress physically in your hand today, how much we've progressed. So moving forward in time slightly, some of the people who've been around a slightly longer would probably remember the Cray technology in 1976. Cray released the Cray 1. But again, just to give you an idea, the Cray 1 was hand-built, cost $10 million, had 32 megabytes worth of memory. Again, remember how much is in your phone today, and was capable of 160 megaflops. Now remember that number because we'll come back to that. And really, these are just to illustrate of where we've come from. And these machines, a lot of them were very much being designed for computational fluid dynamics. And even today, on the largest computers in the world today, the usage of those computers is actually dominated by computational fluid dynamics. So they're very much their major use is still very much in the same scientific area. So what does that look like extrapolated to today? So this is slightly a complex graph. You'll be familiar with the very top line. So the very top line on that graph is what's known as Moore's law. So where the numbers of transistors on the processors that we have in our computing devices is doubling every 1.5 to 2 years, and that forms that line at the top. And interestingly, that's a trend which has carried on. And yeah, not forsaking any changes in the economic circumstances, the science and the physics behind Moore's law looks to continue, at least for a while yet. It's not dead. Economics might drive the rate slightly differently, but the technology and the underlying science is still valid and still progressing on that line, which is quite amazing. The ones which are sort of more of interest to an application point of view, so for people writing applications, writing modeling software, writing CFD applications, are probably the two bottom line, the 2 lines below, the blue line and the green line. So the blue line very much is talking about single thread performance, and that was something which over the 1980s, 90s, and the early 2000s was something that we relied upon for our application performance. And really, as you can see, that line pretty much followed Moore's law. So every 2 years, you could buy yourself a new computer, and your CFD code will deliver you results twice as quick. And that's essentially what was happening over that period. So you could fairly rely on Moore's law to deliver that performance. More recently, since sort of 2005 onwards, that hasn't happened. And as that line sort of forecasts, that is dropping off, and that trend there's going to be some very small kicks in it, but ultimately that trend is correct. That single thread performance has effectively hit a plateau. Some of that's due to physics and the limitations of some of the materials which are used. And again, the same things are related to frequency. So frequency has very much been driven by how much power these things are computing or consuming. And in principle, that's pretty much the frequency and the typical power. The main limitation factor there is the fact that the power density is getting so high. And even at the extreme scale, the power density, so the power per unit area, was getting close to the power density of the surface of the sun. And as you can imagine, there aren't that many materials that can tolerate that kind of power density without totally melting or consuming themselves. That's an interesting view in terms of where the technology has gone in terms of performance. But this particular slide gives you what does that mean from a point of view of money, which I suppose from an industry point of view is something which is more relevant. Since the early 90s to today, there's been 15,000 times improvement in terms of the dollar per flop. So for every dollar we used to spend in 1994, if we spent that today, we should have an application which runs 15,000 times faster. My question to the community, I suppose, are we really realizing that kind of performance? Are our applications really benefiting from that 15,000 times improvement? I'd suggest not, but open to debate on that particular topic. But our ability to leverage that massive improvement in dollar per flop actually should enable us to do more science and allow, from an industry point of view, allow us to either design better products or exploit these kind of technologies in a much more deeper fashion within our engineering process. The other trend, which is also affecting the dollar per flop, whether you call it HPC in the cloud or HPC plus cloud or HPC as a cloud, they're very, very different, very sort of a lot of names talking about things pretty much exactly the same thing, is very much a situation where you can get access to, in our particular case quite generically, let's call them flops, or floating point operations, effectively on an on-demand basis. So you're not investing large amounts of capital in computing infrastructures, which might at sometimes of the year be sat there underutilized, where you effectively can access these as and when you require. And in some situations, that reduction in dollar per flop can be very dramatic, and you can see cases where that adds an order of magnitude in terms of reduction, in terms of the dollar to flop benefit that you've seen in that previous slide. So again, that's a massive change in the way we can access computational infrastructures at ever decreasing prices. One of the challenges here, obviously, is potentially related to security. But I'll sort of suggest really that security is a balance between risk and reward. If the reward is high enough, you'd probably be tolerant of greater risk. And there's various computing infrastructures out there which either are extremely cheap, but they are risky, or at the other end are very expensive or extremely secure. And there's everything in between. So that decision really can be made as and when. So if you're doing a research topic or an open test case, actually the risk is pretty low, so I could actually use a cheaper system. If I'm doing something which is highly commercially sensitive, or if anything government sensitive, then actually I'll then be opting for the more expensive solution. But the solutions are out there, so it's matching solution to application and use case ends up delivering that reduction in dollar per flop using these kind of infrastructures. So where are we today from a computing point of view? So I'll just sort of dive down a little bit deeper now into the underlying technological trends which are driving sort of the progress behind some of those numbers that I've mentioned. And I tend to talk about this as sort of being a parallel heterogeneous epoch. So prior to 2005, we were very much in a world where you had a single processor type, and you were computing on that, and that might have been a Cray, it might have been a silicon graphics machine, it might have been a a DEC Alpha or even sort of Intel Beowulf clusters, the world today is much more mixed, where there are sort of setups which could be highly tuned, very specific applications, and there's a huge choice in terms of processors, so that you can be matching processors to a particular application is something which is possible today. So, just reminding you what's in your pocket again. The iPhone 6, something which most people would have heard about. The combined, and I would say this very much, that 13 gigaflops that you can see there is the combined performance of the processor and the graphics card on that device. And that's for under $40. And I'll just remind you of we were in the hundreds of megaflops on the Cray, and that was basically charged out at about $10 million. So the progress from 1976 to today is immense. You have in your pocket something that even at the turn of the century we didn't actually have on our desktops. So the technology is moving at a tremendous rate, and the cost is dropping immensely. And it's very much been driven by this market. It's been driven by the mobile market. And actually HPC isn't the main driver in terms of the underlying technology. The main technology developments have been driven by this type of market. So very much we as a community who need HPC and will consume huge amounts of HPC, we need to be cognizant of this, because ultimately we need to be able to leverage the kind of technological trends which has been driven by that particular industry, because we're not anywhere near big enough to be able to steer the technology direction, given the size of the markets and the size of investment going into these types of devices. You might have heard of these particular processors. So these it's a processor from NVIDIA, as it says there, the most advanced GPU ever made. It's pretty much out of date, to be honest. There's a new one just about to be released. But this is technology which has been driven by the gaming market. It isn't something which has been developed very specifically for HPC, but actually has found a home in the world of computation, as the world of gaming is driving to more higher fidelity physics. The capabilities to do more complex computations that drives the ability to simulate those physics in real time is something that we can leverage within the modeling community. And that has driven some step changes in terms of capability. And effectively what it does is presenting you a device here which got thousands of cores on it. So this is effectively what you have within your laptop on steroids. It's huge numbers of cores. Each of the individual processors, as those graphs were telling you previously, are of lower frequency, they're of low power, they don't perform as well, so the performance is very, very much lower than the processors you've got within your laptop. But the combination of all of them together is immense. So then it drives you to try and exploit that kind of capability. And I'll come back to some slides with some more details about where the technology is going in that space. To really give you a balanced view of this is Intel's view in this particular world. Again, this is their Knights Landing processor, which is soon to be hitting the stores. Again, this is Intel's take on these high core count processors, what I would call many core processors. So I very much see whether it's a GPU or these are many core processors. So you're in sort of the hundreds to thousands, and you will eventually see sort of tens of thousands of cores on a single piece of silicon, very much sort of heading in the same direction. Intel and NVIDIA have taken a very different approach to how they extract performance out of the cores, and that really then lends itself to that different applications and different algorithms will suit the different types of processors differently. And so this is really just reinforcing this whole heterogeneous world where ultimately you could imagine the CFD computer of the future is very much going to be a mixture of all of these processes. Some of them being very good at mesh generation, some of them being better at visualization, some of them being better at solving equations in a particular form, and others in different forms. So you'll have this mix in terms of the system. So really going back to where the GPU technology is, the majority of GPU clusters out there today, which make use of, can leverage this type of hardware, are very much made out of the Kepler generation of technology that you can actually see there. Pascal, the one that's highlighted, is due out shortly, and I really just wanted to highlight a couple of things that technology is trying to push. You'll see the word there, mixed precision. So I'll come back to algorithms. In our world, we very rarely exploit mixed precision. So most of our algorithms either run purely in single precision or purely in double precision. We tend to put very little thought into the underlying numerics and exploit mixed precision architectures, partly because the hardware wasn't very good at supporting it. But Pascal is very much trying to open up that possibility. So I think that will require us to have a new think about how we implement algorithms to make best use of that. The other one highlighted there is 3D memory. Now, as we get more heterogeneous in terms of what we can compute on, what's also happening is the complexity of what these devices are also increasing. So now we've got increasing depth in different types of memory that we've got access to. So how our algorithms make use of this, we need to have a greater think about it. It's not something that we can just implement and the compiler will automatically place our arrays in the right piece of memory to get the best performance. It's something that will require some thinking. And if we do think about it both from a point of view of the numerics, from mixed precision, where we place the data, we can then start to extract the performance and effectively extract that value. We can get closer to getting that sort of 15,000 times improvement in terms of dollar per flop, because by not doing so, we will never realize that value that these technologies potentially deliver to us. The other side of the technology, which sort of, again, driving, and this is very much true for whether it's Intel or GPUs or whichever else is coming away and being developed in the future, is very much how these things are connected together. CFD, by its nature, is something which has to be solved. We're solving at scale in lockstep, so it's very much dependent on how fast, less so in terms of bandwidth, but how fast we can talk between our collaborating processes which are solving our equations. So our ability to link these processes together with very fast interconnects is key to working at scale. And as you can imagine, the more cores that we put on each of these individual devices, and the more things which are talking across these networks, the better those links have to come. This is one particular technology from NVIDIA. Intel also proposing their own version of these types of high-speed interconnects, because that's what's going to enable us to run at scale. And the ultimate aim in this space at the moment is to be able to run at exascale. But yeah, it'll be amazing to see whether our current generation of CFD algorithms can be pushed to that kind of size. But so very much complexity in terms of memory, mixed precision, high-speed interconnects, which are different to what's available today, is going to be things which are going to be hitting the streets in the next couple of years. And we really need to be ready for it as a community if we really want to extract that value from these developments. So I'll finish off really with I suppose a comment on the final statement from NASA in terms of algorithms. I have been referring to sort of, as we've been going on, in terms of how best our algorithms need to be effectively modified or be cognizant of the underlying hardware. But there's some fundamental questions that we still need to ask ourselves as in this highly parallel world, and I'll come back in conclusion and give you a real world example of how this sort of manifests itself. So this is what I've been calling, I suppose, the computing and algorithm dilemma. The two equations you can see on the screen there hopefully are familiar to you, and they form broadly the two main ways that we tend to solve the Navier-Stokes equations in CFD. The first one, which is usually termed the explicit method, where we're marching our solution in time based on an approximation of the right-hand side, but using the old time steps. So as you can see there, R of WK, so we're using an approximation using the previous time step to give us a march in time, which is solved using an iterative solver, and we'll march that, and you can use methods like laundry cutter to solve these, and we can march that forward either to a steady state or even to an unsteady solution, to a time-accurate solution. The second line you can see there is the implicit form of solving exactly the same equations, and really that's derived from the fact that we're trying to use a better estimate of the solution when we calculate the right-hand side. So not using our old solution, but we're trying to improve that estimate to try and march our solution in time, and that's typically solved using linear solvers. Now, in the world today, in terms of what's best fits to our computing infrastructures, the world of explicit solving is highly parallelizable and is something which is relatively simple to do and works very well. And I'll give you some examples of that. Getting linear solvers to work efficiently on highly parallel architectures is another whole world. So it's very difficult, and it's very difficult more specifically because the preconditioners that you typically use to improve the ability to solve the conditioning number of the system actually are very hard to parallelize. So now you're in a dilemma. The implicit way of solving gives you something which gives you a superior numerical performance to an explicit scheme. You do more work per cycle, but you potentially get there faster. The explicit scheme might not be well suited for certain physics, but parallelizes very well. So which one do you pick in a world where you really want to be in a highly parallel, or be able to parallelize in a highly parallel fashion, but without compromising your numerical performance? So in the ideal world, we'd come up with a mixture of the two. The jury is still out. So at the moment, there are cases where even though the numerical performance of an explicit scheme is pretty poor, but because of the speed-ups you get from parallelism, it will give you a solution quicker than solving it using an implicit scheme. So it adds a degree of complexity in terms of choice. How do we solve the particular sets of equations that we have? And Dirk was sort of referring to that in his first talk. When it comes to combustion very much is solved typically in the implicit fashion because these are extremely stiff equations he's solving, and you really need the numerical performance of an implicit scheme to allow you to solve that. But that then becomes a real bottleneck in terms of performance if you want to get these answers out quickly. So we really need to start considering either coming up with new preconditioners which parallelize better, or ability to combine the best of both worlds to be able to exploit the trend in computational hardware. But finally, just to give you an idea of actually what I'm talking about here isn't something which we sort of dreamt up. Got to disclose here this is a code that I have written over the last couple of years. This just gives you an idea on a standard test case. This is a NASA Common Research Model, which is used as part of the NASA Drag Prediction Workshop. And what I'm showing here is strong scaling. So the size of the case is 138 million cells, equivalent to about 1 billion unknowns. We're solving the full RANS equation, so I'm using a two-equation turbulence model, so I'm using K omega SST in this particular case. So we're not compromising in terms of the physics that we're trying to solve, and it really just gives you a feel for the kind of speed-ups that this new kind of highly parallel technology is going to deliver to you. So what you're seeing on the vertical axis is a speed-up factor, and that speed-up factor is relative to a single core of an Intel Ivy Bridge processor. And on the bottom axis, you're seeing an increase in terms of number of cores or number of devices. So my number of devices is, in this particular case, an NVIDIA GPU. They're both log scales, so you'd expect them to effectively give you straight lines. But effectively, the take-home message here is that you're ultimately getting a 30x speed up from going from one single Intel core or Intel device to an NVIDIA GPU. Now you might say, okay, that's fair enough, but the NVIDIA GPU is costing you a lot more than an Intel processor. But even when you factor in the costs, the increasing cost of the underlying hardware, you're still a factor of 4 ahead. So in terms of cost to solution, which might be of interest to somebody from industry, or the ability to run more cases on the same machine, which might be something potentially of more interest to from an academic point of view, they both deliver in doing so. The caveat being is that you need to be able to exploit the underlying hardware. In this particular case, at any moment in time, there's 100 million threads running. At the very largest case that I'm running here, there's 100 million threads computing at any moment in time. So there's a lot of work, and that's the kind of degree of parallelism that you need to be able to expose to the underlying hardware to make use of those devices. But overall, it provides a massive step, and this is very much true of whatever the hardware which is going to be coming out in the future. What we know, they are going to be parallel, and they're going to be of increasing size from a parallelism point of view. So we need to be prepared to be able to exploit them quite broadly. And that's all from me. Thank you.